Everybody. This is Professor Lee. Welcome. Here, I'm going to start a project where we learn statistics, the real statistics. And a lot of technical matters becoming easier and more available because of this generative AIs, and they write codes for you. So it's very important that you have an understanding of what's being done or the codes and what is the theoretical basis for such codes to exist. So the knowledge beneath what's happening or the knowledge above of the phenomenon, that is what I think we need in this age of computer and AI. So I'm going to start some basic study for computational and statistical inferences. So we'll look at this book together. It's going to be quite a lot, but I don't know how many sections it'll be. I have created, with the help of AI, about 200 pages of PowerPoint slides. So we'll look at that and then I'll go over this textbook together. Okay, so let's get started. Firstly, the textbook is this Trevor Hasty, Computer Age Statistical Inferences, the Algorithms, Evidence, and the Data Science. So there are a lot of, there's 4 words written by great professors. How and why is computational statistics taking over the world in this serious work of synthesis that is also fun to read. Afron and Hasty, 2 pioneers in the integration of parametric, non-parametric statistical ideas, give their take on unreasonable effectiveness of statistics and machine learning in the context of a series of clear, historically informed texts. Also, it's talked about Rob Koss from Carnegie Mellon University. This is an unusual book describing the nature of statistics by displaying examples. Explains this why. Okay. The field has evolved over several decades and is adapting to rapid increase in the available compute power. So their perspective is when they say, roughly speaking, algorithms are what statisticians do and inferences is why do them. So the book explains why, and that's explaining the purpose and progress of a statistical research through a close look at many major methods. Okay, and so on. So you can probably get hands on this full text of this textbook, about 495 pages. Absolutely brilliant book, beautifully written. So all these compliments. So let's take a look whether this is any, there's a truth to all these compliments. So the book title is the Computer Age Statistical Inference. So in Korean, it's called 추론. Okay, so what is 추론? What is statistical inference? And we're going to study that. Okay. So maybe, we know now by with AI, they talking about training AI, and also they talk about what? Inference AI, reasoning AI, and all of that. So actually, it's this book written by Bradley Aflon and Trevor Hasty of Stanford. So its stated audience is the master level or the graduate level statisticians and first-year doctoral students. It contains several hundred equations. If you open it at random, you will land on something incomprehensible, and you might will be able to feel that. But we're going to read it anyway. Does that make sense? Over some time, and by the end you'll understand its arguments, not its derivations or formulas, but you will understand its arguments. Okay, those are different things, and the difference is the entire premise of this project, lecture project. And here's why: a student of literature, because a lot of my students are what's called the 문과. So they are students of literature, history, economics, and business people. Sometimes philosophy, and all of them belong in this room. So its book is about a question where you were trained to ask, what does the evidence entitle us to claim? Okay, when you have a data, when you have a sample and data, it's a subset of the population you want to project your conclusions upon. And so when you have a bit of evidence, then using some tools, knowledge tools or frameworks that you are trying to find a statement that this evidence projects, and also be able to project it onto a bigger set of population. So that's what Alfron and Hasty call inference. And they spend 493 pages showing that in a harder order, more contested than anyone outside in the field imagine. So if you are challenged, you might want to go and read the whole textbook. But this is a sort of try to let us open up for the world of statistics and be able to discover the jewelry or the gems and the power that it gives to you. Okay, so statistics operate one step back from nature, most often interpreting the observations of nature scientists. Without nature to serve as a disinterested referee, we need a system of mathematical logic for guidance and correction. Okay, so this is from the book's preface, and I want you to notice that what has been conceded. The authors are telling us that their discipline is not a natural science. Physics has nature to settle its disputes. When the experiment disagrees with you, you lose. Statistics has no such referee, because statistics does not study the word directly. Okay? It studies observation that other people made without the word. So there is a word for a discipline that interprets the records of experience without direct access to the thing recorded. And that word is hermeneutics. That is in Korean, 해석학. So you have all done this. You have argued about a document licenses. You want to conclude knowing the document is partial. Okay, and that whoever produced it has purposes, and that no appeal to the thing itself is available. You still kind of make statements. Okay, the value of it, the validity of it. So the claim I'm making on the first day is not that statistics is easy. It's not that you will become statisticians. So this book is a work of interpretive theory. Okay, interpretive theory carried out in an unfamiliar notation, and that interpretive part is yours already. Moving on, page 3. You already live inside this book's consequences. That's the argument for reading a statistics book you cannot fully compute. Every recommendation you get from this AI machinery, credit scores, your medical prognosis, or hiring filter you meet for job market, there is an algorithm from part 3 of this textbook. So public conversation of AI is conducted most entirely in the vocabulary of chapters 17, 18, random forest boosting deep learning, by people who have not learned chapters 1 through 5, which explains why and any of it should be believed. So, what does this evidence entitle us to claim. What does this evidence entitle us to claim? So this is a question. It's not a mathematical question, but it is a critical question having relevance to the real world we live in. So Efron and Hasty themselves place their subject, us, at the triple point of mathematics. Triple point of mathematics. 수학의 삼각점, empirical science, 실증, and mathematics, 수학, and philosophy, 철학. Okay, so if you're not in 이과, you're 문과, still you know the philosophy and interpretive hermeneutics. So let's get ourselves used to mathematics and empirical science, and by marrying these together, you'll be understand what inference is and how we use the inference. Okay, so take a look at the 3 rules for reading mathematics as prose. Okay, when you see mathematics, it's not different. It's still language. It's like prose. Okay, 수학도 산문, 글과 같이 읽으면 된다 이 말입니다. Number 1, every formula is a sentence. 공식은 문장과 같다. It has a subject, what's being computed, 주어, and verb, the operation 연산, and object, from what data. Okay, so we'll name all 3 before showing symbols. So it's exactly like a literary sentence: subject, verb, object. Rule number 2 is that the equal sign word is. Okay, when you see the equation and the equal sign, the 2 lines, that represents is. And the summation sign, sigma, is a phrase add up over all cases. And the hat sign means it's an estimate of something. So it's never the truth, never the real thing, but it's the best estimate of something. Okay, rule number 3, when you meet a formula you cannot parse, ask, what would change if the formula were slightly different? Meaning lives in the contrast. Meaning lives in the contrast, exactly in a close reading of a poem. So worked instance, the simple mean is written as x bar equals parenthesis 1 over n, parenthesis close, sigma xi times xi. Okay, so in English, it's a like I said, it's a sentence. So English, it means add up everybody's value, divide by how many people there are. Okay, so you have known this since primary school. The notation is not a new idea; it's just a new handwriting. Okay, so this is something, just different expression of something you already know. All right, so minimal glossary of symbols. Some of you have decided at 15, 16, maybe I'm not a really mathematics person, but I want to address this directly rather than pretend it's not in the room. That's the elephant. The decision was almost certainly made on the basis of speed at arithmetic under time pressure. So how quickly you could manipulate symbols in exam room, and that skill has very nearly nothing to do with what this book asks of a reader. Okay, so being able to solve a lot of questions under time pressure, that doesn't make you a real mathematician. Actually, the real mathematics professor, when they take what's called the college entrance exam, they get like 5등급, 3등급, yeah. So at the highest level, it's not about time pressure, it's about you having aim for time, but understanding why this matters, and what problem is it solving. Those things matter more. So even Einstein said the reason he's so good at physics is just he stays at the problem longer than anybody else. So, what this book asks is that you hold a complicated argument in mind across many pages, that you notice that when a claim has quietly exceeded the evidence offered for it, and that you ask what a technical term is actually doing rather than accepting it as a declaration. So, those are the skills of a close reader as you've been trained in them for years. So, you'll meet about 30 formulas across this project. Everyone will be translated into an English sentence before it appears on the screen. And the English sentence is examinable content, something that you can examine and understand in meaning, because it's like words, it's sentences. So you were not, it's just different symbols and manifestation, but it's same as you reading prose in a story. So you will not be asked to compute anything ever, but you'll be asked to say what computation claims and whether the claim is warranted. Okay? Warranted as truth. Okay. Moving on. So the one distinction that organized all 21 chapters, what a nice number, 21, is that okay, so let's try to differentiate the words written here. Algorithm and inference. So algorithm is the recipe. The recipe was the statisticians actually does to the numbers. Fit a line, grow a tree, train a network, inventive, fast-moving, glamorous recipe. Inference is the warrant. Why anyone should believe the recipe's output. Slower, more careful, always arriving late. So Efron's and Hasty's own summary, algorithms are what statisticians do, where inference says why they do them. Okay, again, algorithm is what they do. Inferences is why do they do them. So their image for the relationship is a tortoise and a hare, 거북이와 토끼. Then they add the sentence, they should frighten us. Modern computation has bred a bionic hare. The recipe now sprint and justifications still walk. Okay. 한국말 설명하자면은 바이오닉이라는 거는 그 600만 불 사나이 같은 그런 아주 힘센 인간이죠. 그래서 지금 알고리즘은 엄청나게 달려가고 있는데 justifications 이게 왜 중요하고 이게 진실이 얼마나 수렴하는가 이런 것들은 천천히 tortoise처럼 거북이처럼 천천히 가고 있다. So our job as a humanist, I say all the social science and humanities majors in the age of AI, is to be an advocate of a tortoise. Algorithms move fast, but we are like tortoise. We put everything together and then bring out the real meaning for the humanity. Okay. Next. Okay, so the shape of a book. 3 parts. Part 1, Part 2, Part 3. So Part 1 is the era before computers came along. So it was up to 1950s. Talk about classical inference with the very little data and no machine. What may we honestly conclude? Okay. And the age 2 is early computer age, 6 to 14 chapters. So it talks about bootstraps, empirical Bayes, survivor, or cross-validation. Now, the characteristic question is, now that the machine can repeat a calculation a million times, what new honesty becomes possible? In the 21st century, era 3, chapters 15 to 21, FDR, Lasso, Forest, Deep Learning. So the characteristic question is how we can now ask thousands of questions at once and predict brilliantly, but can we still say why we believe it? Okay, so that's the the etymological question, and that's where we spend most of time here. Okay. And the course map, you can take a look from chapters 1, algorithm and inference, chapter 2 to 3, frequent test and Bayesian, chapter 4 through 5, Fisher likelihood families, chapter 6, empirical Bayes, chapter 7, James, Stein, and Rich, chapters 8 and 9, regression trees survival, chapters 10 and 10 through 12 is bootstrap jackknife cross validation, 13 through 14 objective Bayes and MCMC Monte Carlo, and 15 is large scale testing FDR. 16 through 17 is sparsity, forests, and boosting. 18 through 19, neural nets and deep learning. 20 to the end is inference after selection. Okay, so the one thing you should carry away for each section is given on the right column. Okay, so interesting summary of the whole book. Now, on mathematical anxiety, how are we gonna address it directly? Okay. So algorithm is a recipe. Inference is warrant. Efron Hasty said that algorithms are what statisticians do. Inference is why do them. So then they offer an image for the relationship between the two, right? So I think we addressed here. Now, how to read a quantitative paper without doing the mathematics. This is a key trick. You learn to do this and you will not give up on reading mathematical or technical paper. Okay? How do you do that? Read the abstract, then skip immediately to the tables and figures. The prose tells you what the authors concluded. The tables tell you what they found. These are not always the same document. In the method section, look for 4 things: how many cases, how many variables or outcomes examined, whether the analysis was specified in advance, and how the model was validated. In the results, note the effect size before p-value. A tiny effect with an impressive p-value is a statement about sample size, not about importance. In the discussion, watch for the drift from associated with to causes, and from in this sample to in general. So the drift is usually gradual and always consequential. So you can do all 4 of these today before we have converted anything. Okay. Moving on. Assessment and expectations. So walk the table row by row. The right-hand column is part we pay attention. So participation component, reading responses, translation exercises, and this is something that I would have done if it were a real class, but since this is an online lecture, just moving on. Okay, so slide 12. Without nature to serve as a disinterested referee, we need a system of mathematical logic for guidance and correction. Again, without nature to serve as a disinterested referee, we need a system of mathematical logic for guidance and correction. Okay. Section 1. Algorithms and inferences. This runs from slides 13 to 31. Okay, so chapter 1 makes a claim before it offers any evidence. So let us state the claim first and watch it get proved twice. The claim is that the recipe always comes first and justification arrives afterwards at a second level of statistical consideration. So that's not an accusation. That's not an accusation. It's a description of how any practical discipline develops. So physicians heal people for centuries before anyone understood the infection. Our orators persuaded audiences long before Aristotle wrote the rhetoric down. Practice precedes theory almost everywhere, and there's nothing to be shameful in it. But it has a consequence that matters enormously right now. At any given moment, there are powerful tools in wide use whose warrant is genuinely unsettled. So that moment is the present, and the tools are called machine learning. So chapter 1 proves the claim twice. Once for estimation, which asks how much, once for testing, which asks whether there's anything there at all. And those two verbs are the whole of what statistics does. And I'd like to unify everything you meet this term under one or the other. Okay. Now, a study of kidneys and a question about donors. So it's a real data. First example is study of kidney function. 157 healthy volunteers, and for each one, two numbers, age in years and composite score of how well their kidneys are working. Okay, so the basic pattern is not in dispute and requires no statistics to see. Kidney function declines with age, and the scatter point slopes downward. Anywhere can take a look. The question is that matters is that whether, but how fast, crucially, how confidently we know the rate. So I opened the book, figure 1.1. This is a graph. X-axis is age, the y-axis is kidney fitness, TOT, for 157 volunteers. So you will see if the points, each individual. This line is a linear regression fit showing plus minus 2 standard errors as selected values of age as a vertical line crossing the statistical regression fit. So the rate of decline and our confidence in it is now doing the moral work. A regression slope has become an ethical instrument. It helps decide whose kidney is permitted to save someone's life. Hold on to that, because a recurring temptation in this subject is to imagine that it is bloodless, but it's not. It's a line on the graph deciding who may donate an organ and not allowed to donate the kidney. Okay, so this model has real consequence. Okay, so if you're interested, there is this regression model 1.3 with one least squares model with one independent variable, which is age. Okay. So least squares is drawing the line. Beta 0 or beta naught 0, like beta naught hat and beta 1 hat. So here beta naught hat is the intercept, the fitting level at age 0, and beta 1 hat is the slope. How much function is lost per additional year of age? So the hat means it's estimates, not the true value itself, but it's the best estimate value. So how is the line is chosen? Is least squares. So take every possible line for each, measure how far each of the 157 points sits above or below it, and square those instances and add them up. Keep the line where the total is the smallest. So why squared and not simple distance? Squaring punishes large misses far more than small ones. And the historic reason, it makes answers solvable with pen and paper. A choice of pre-computer age still with us. Note what has just happened. An algorithm has been specified completely and not one word has been said about whether we should believe its output, right? So that was least squares as an algorithm. Now, what textbook theory gives you free of charge? Because least squares is mathematically simple, 19th century theory can hand you the accuracy of that line free of charge. No computer requires a standard error for the slope, error bars around the fitted values. All of it can be derived with a pen and pencil on a paper. Let me say what standard error means because I use the phrase for the rest of the course. If we could repeat this entire study, go out and find 157 fresh volunteers again and again, how much would fit the fitted slope jump around? A small standard error means a stable answer. A large standard error means a study barely pinned anything down. So this is a magnificent bargain. Inference for free. It is the intellectual word of part 1 of this book, but every bargain has a price, and here's the one. The free warrant is available only for procedures simple enough to be analyzed mathematically. The moment you use a clever algorithm, the mathematics becomes intractable and the warrant vanishes. Okay, so simple algorithm gives you this benefit of free warrant. You can always check, you can do the hand calculation and check. Clever algorithm, complex ones, there will be no warrant unless you invent one. So 16 of the remaining 20 chapters are the work of inventing the warrant for clever and more advanced algorithms. The problem with straight lines is, again, nature is not linear. Okay? So a single straight line forces one constant rate of decline across whole lifespan. Biologically, that is a strong and probably first assumption. Decline may be gentle at 25 and stiff at 65. Let's go back to the text, and here is the straight line of regression model. But there are many different ways you can draw a model line, estimated model line, and one of the such lines are nonlinear. Okay, so 25 maybe not so much of decline with age, 25 to 30 something, but with 60 there are quite a lot, of decline, very steep decline, 60s. Okay, so it's a polynomial model fit to kidney fitness data, and with the plus minus 2 bootstrap standard deviation. So it's called the modern computer-based algorithm. Lois produced something bumpy regression line in figure 1.2. So Lois is an algorithm. This is an algorithm that moves its attention along the x-axis, fitting the local polynomial curves of differing degrees to nearby xy points. And the 1/3 in the call 3 lowest x, y 1/3 is how it's expressed. So repeated passes over the x-axis refine the fit, reducing the effects of occasional anomaly points. The fitted curve in figure 1.2 nearly linear at the right, more complicated at the left, where the points are more densely packed. It's flat between ages 25 and 35. Potentially important difference from the uniform decline portrayed in figure 1.1. So there's no formula such as 1.2 to infer the accuracy of the lowest curve. Instead, a computer-intensive inferential engine, the Bootstrap, was used to calculate the error bars in figure 1.2. Okay, so using Bootstrap, they calculated error bars. A Bootstrap data set is produced by resampling 157 pairs XI, YI from the original 157 with replacement. So perhaps X1, Y1 might show up twice in the Bootstrap sample. X2, Y2 might be missing. X3, Y3 present once, etc. So applying lowest to the Bootstrap sample generates a Bootstrap replication of the original calculation. So 25 Bootstrap replications of lowest is presented here. Okay, going back to the case. So straight line forces one constant rate of decline. May not really work with the data that the decline is gentler at age 25 than 65. So the computer age answer is, instead of one big whole fit, let's have a localized fit, local fit. So Efron and Hasty uses algorithm called LOWIS, locally weighted scatter plot. So LOWIS, locally weighted, LOW, scatter, so S, LOWIS. And now LOWIS works in one sentence to estimate kidney function at age 40. Look only at volunteers near age 40, weight the nearest ones most heavily, fit a letter line to just those and record its value, then slide along and repeat at every age. So the result is a flexible curve and a curvic one, and follows the data wherever it goes. It's a better description of the word, better description of what's really happening with the age increasing. So it's also an algorithm that no 19th century mathematicians could analyze. So we have both accuracy of description with the loss of our free warrant. What now? So Bootstrap. We have a flexible curve that describes aging kidneys much better than a straight line. And no mathematical theory can tell us how much to trust it. What did you do? Here's what Efron did in 1979, and it is one of the genuinely surprising ideas of 20th century. The honest question is, if we ran this study again, how different would the curve be? The honest obstacle is that we cannot run it again. There are 157 volunteers and there's no more money. So Bootstrap's move is audacious. Treat the sample as if it were the population and draw a new sample from it. Take 157 pairs at random from your own 157 with replacement. So volunteer number 1 might appear twice. Volunteer number 40 might not appear at all. This fabricated data set is a Bootstrap sample. It's not a real one, not a real sample, but not real people, but it's a kind of thing that word might plausibly have handed you instead. So fit the curve to it and you have a second curve you never observed. Do it 250 times. Efron and Hasty plot the first 25 and they form a fuzz band around the original. So where the band is narrow, its estimate is solid. Where it is wide, the curve is guessing. The spread of those replications at any given age is the standard error. Inference has been obtained not by proving a theorem, but running a simulation. This is a computer age in one picture. So why the name? Bootstrap. To pull oneself up by one's own bootstraps. To accomplish something impossible without outside help. The name is a joke about the absurdity of the method, which generated new evidence about the world using nothing but the evidence we already have. So that it works, and it demonstrates it does, and is one genuine surprises of the 21st thought. Okay, moving on to next case. Leukemia. Then the question of statistical surprise. The data are 72 leukemia patients, 45 with all ALL, acute lymphoblastic leukemia, and 27 with AML, acute myeloid leukemia, the worst prognosis. So for each patient, genetic activity measured across a panel of 7,128 genes. So let's start with the single gene, number 136. Average activity in the ALL group, 0.752. And the other AML group, its numbers run up to 0.95. The AML patients show more activity in this gene 136. So the question every reader asks is it is the right question? Is that the difference real or is it not? Or in the phrase Efron Hasty themselves use, a statistical fluke. Okay, is it a real difference or is it a statistical fluke? Which means it looks different, probably maybe not. So note that this is a question about warrant, not about the numbers. So numbers are not in doubt. What is in doubt is what they entitle us to say. Go back to the textbook PDF and it shows the ALL scores of one group, AML scores another group, and their means are different. It looks different. So it is represented as with a bar above, X bar, that's the average, that's the mean. So the perceived difference, is it genuine or statistical fluke? So in order to answer this question, you can use a two-sample t-statistics here and the standard deviation in the denominator, and you take the subtract the mean difference from one group to another. Now, dividing by standard deviation allows us, under Gaussian assumptions, it will be discussed in chapter 5, to compare the observed value of t with the standard NER distribution. In this case, instead of the normal distribution, students' t distribution with 70 degrees of freedom used. Okay, 분포곡선, t 분포곡선, and we obtain t equals 3.01 from this calculation of formula 16, which should classically be considered very strong evidence that the apparent difference 1.5 is genuine. Okay, so in standard terminology, the two-size significance level is 0.0036. A small significance level of p-value, generally using a threshold of 0.05. A p-value less than 0.05 is a statement of statistical surprise. Something very unusual has happened if in fact there is no difference in gene 136 expression levels between the ALL and AML patients. So we are less surprised by t equals 3.01 if gene 136 is just one candidate out of 1,000 that might have produced interesting results. So that's the case here. Okay. So this is the case. Figure 1.5 shows histogram. So what is a histogram? Looking like this. Okay, here and there, histograms of two different groups. And the panel was 7,128 genes. Where's the figure 120? Yeah. So two sample T statistics for 7,128 genes. Humans have about 20,000 genes. The leukemia data. The smooth curve is the theoretical non-density, nerd density, theoretical nerd density of the T statistics. And 3.0 is about here. Okay. So large numbers of candidates, like over 7,000 genes total, and the gene 136 is just one of them. It will produce some large T values even if there is really no difference in genetic expression between AML, ALL patients. The histogram implies that the study there something wrong with the theoretical nerd distribution. Students T with 70 degrees of freedom, the smooth curves in figure 1.5 is much too narrow at the center, and where presumably most of the genes are reporting insignificant results. So we'll see in another chapter, chapter 15 is first discovery rate, which is FTR. First discovery is that when you find something as significant and positive when actually there is no significance differences or statistical significance there. So a low chance of crying wolf over an innocuous gene requires T exceeding 6.16 in AMR study instead of 301. Okay, so only 47 out of the 7128 genes make the cut. So first discovery rate theory is an impressive advance in statistical inference, incorporating Bayesian, frequentist, and empirical Bayesian elements as a necessary advance in the scientific field where computer-based technology roughly presents thousands of comparisons to be evaluated at once. Okay, there's one more important thing to say about algorithm and versus inference but statistical cycle. Important new algorithms often arise outside the world of professional statisticians. Neural nets, support vector machines, and boosting are three famous examples. None of this is surprising. New sources of data, satellite image, for example, medical microarrays, inspire novel methodology from the observing scientists. The early literature tends toward the enthusiastic with claims of enormous applicability and power. Textbook, now coming back to the slides. So the T statistics, when we measure, using it as a measuring surprise, there's a surprise. 3.01 T-score. That looks significant, but there is a context to it that humans have many genes. So genes 136 just one out of like 20,000 and what all the genes they have now under the microscope, that's about 7,000 genes. So with the histogram against the backdrop, the T equals 3.101 stops looking remarkable. Okay, so the classical theory then converts this into p-value of 0.0036. No true difference in the gene between the two groups. If there were no difference, data at least this lopsided would turn out about 4 times in 1,000. Therefore, Inference and Hastie's gloss on this is more careful than the most textbook manage. I want you to adopt their wording. A small p-value, they say, is a statement of statistical surprise. It's a surprise, but not proof. Not the probability that the hypothesis is false. surprise under an assumption. So by the conventions of 1980, this would have ended the discussion. Gene 136 is significant, write it up, publish. But modern science would have a different question. What is the first discovery rate as a new standard of evidence? So except that the gene 136 was not a hypothesis anybody held before the study began. It was selected out of 7,128 candidates because it looked interesting. So Efron has to do the obvious thing, which almost nobody did before about 1995. They compute the same statistics for all 7,000 genes and plot the histogram, which you saw in figure 1.5. And against that backdrop, 3.01 stops looking remarkable, and about 400 other genes exceeded it, roughly 5.5% of them. So now the authors are careful here, and we must be too. This does not mean gene 136 is significant at a 5.5% level. It means the original question was badly posted. They diagnosed two complications. The first is the one you already seen coming. A large number of candidates will produce some large values even when absolutely nothing is going on. So the second is deeper and more unsettling. The histogram is much too narrow at the center to match the theoretical curve. So the mathematical description of nothing happening, the null distribution, the thing, all hypothesis testing measured against, is simply wrong for this data. Okay, sit with that for a moment. It's not merely that we ask too many questions. It's a theory of what science sounds like turned out to be mistaken. So two examples, one structure, kidney and leukemia. So modern answer changes the question being asked. No, not is this gene surprising, but what matters is if I publish this entire list of genes, what fraction of the list will be wrong? So Efron and Hasty give the number for this study to keep a low first discovery rate, a low chance, as they put it, crying wolf over an innocuous gene. The statistic must exceed 6.16. Only 47 of the 7,000 instead of like 5%, 400 of them clear that bar. Okay, so compare the two regimes. The classical threshold admitted about 400 genes. The modern one admits 47, which is to say 9 out of every 10 apparent discoveries were an artifact of having asked too many questions. So the authors call first discovery rate theory an impressive advance in statistical inference, and they know something we will turn to in the 9th section. It blends Bayesian frequentist and empirical Bayes elements. 3 schools that spent 20th century at war cooperating because the problem was hard enough to require all of them. So moving on. The new algorithm. Where the new algorithm come from? Efron and Hasty note without visual resentment that important new algorithms often arise outside the world of professional statisticians. So their examples, neural networks, SVM boosting, these arrive from computer science, engineering, and industry, invented by people solving a problem, not by people proving a theorem. So the tortoise is not merely slow, it's frequently handed a hare it did not breed and asked to certify it after the fact. So this is the condition of intellectual life generally. Practice outruns justification, and the works of justification is done by people who did not get to choose what they must justify. So if that describes your own discipline's relationship to technology, then that's where chapter 1 is. Okay. Now, one exercise. Translate these 4 sentences. Okay, the effect was significant 0.03. If you translate, If nothing were going on, the data, at least this lopsided, would appear only 3 times in 100. It says nothing about how large the effect is or how probable the hypothesis is. Second, we find a 95% confidence interval of 2 to 8. Translation: the procedure that generated this interval captures the truth in 95% of its uses. What's not is there's a 95% chance the truth lies between 2 and 8. Okay, so be able to make distinction, because what it says is not what you think it is. The model explained 87% of variance. Then you should ask immediately on which data. If on the data used to build it, the number is self-assessment and means very little. Okay, we tested 40 outcomes and 3 were significant. Translation: at the level 0.05 level, 2 significant results are expected from pure noise. So there's barely more than nothing. Every one of these translations is available to you now, and none of this requires a hard math. Now, 4 things a p-value does not mean. A p-value is not a probability that a hypothesis is false. The p-value is computed by assuming nothing going on. A quantity computed under an assumption cannot report the probability of an assumption. It's not the probability that the result was due to chance, some error in different clothing. It's not a measure of effect size. With a large enough sample, a trivially small difference produces a spectacularly small p-value. Significance and importance are unrelated quantities. And it's not probability that finding will replicate. Replication depends on the true effect size and the value, the power of next study. So neither of which the p-value reports. And a fifth, a p-value from hypothesis selected out of 1,000 is not a p-value at all at any useful sense. And Gene 136 taught us. So these are some of the questions from session 1. I hope you enjoyed the session 1 recap, table, look, and study. The verb dokimazete on testing and the patience of warrant. So it's a Greek letter. Test everything, hold fast what is good. And from Bible, 1 Thessalonians 5:21. Test everything. Test everything. And hold fast what is good. And let go of what is not good. Okay. Pante, dokimazete, to kalon, katechete. Test everything. Hold fast what is good. Notice that the sentence have 2 halves. The most readers can keep only one. Test without holding fast is corrosion. Holding fast without testing is credulity. So chapter 1 is the first in mathematical dress. The bootstrap is a furnace. First discovery rate is a discipline of releasing only what came through it. There's a warning in it for our moment as well. The hare, the rabbit, is not wicked. It's just merely fast. The passage asks is not we slow the hare down, but we refuse to hold fast to anything the fire has not touched. All right. Thank you very much for your attention. This is the end of lecture 1.